Hi everyone, welcome back to my YouTube channel. I decided to share a project that was designed and manufactured for experimental purposes. And it was created to measure an object, steel ball, so this 20mm ball, or this 20mm wooden ball with 2 bits of tape on it. It was created to test the ball from... Let's try this again. Where'd the ball go? Where did the ball go? Lost the ball then. I didn't lost the ball. I lost the ball. Gosh. Only me. The ball's gone. Right. Hi everyone, welcome back to my YouTube channel. I've decided to share a project that was designed and manufactured for experimental purposes. It was created to measure an object, steel ball and wooden ball, falling through the atmosphere whilst being subjected to external forces. Okay, so going away back to the 17th century now, Sir Isaac Newton's first law states that every object will remain at rest or in a uniform motion in a straight line unless compelled to change its state by the action of an external force. His second law states that every object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This project examines his statements whilst having the capability of accurately measuring each ball's velocity every 100mm intervals, all the way from 1500mm. If the balls were falling in a vacuum, the only force acting on them would be gravitational force. However, I was going to build a vacuum chamber around this project and house the sensors, but I went against it and ended up, I might do it in the future, so I can eliminate air resistance and do calculations on different objects, but I would need really maybe higher distance to test, to experiment with. At the minute I'm currently only working with 1500mm height. So a vacuum chamber would not prove anything other than different objects, materials fall at the same rate as air resistance is eliminated. However, the distance the balls are being dropped is not sufficiently large enough. So air resistance is quite minimal, especially on the steel ball. Okay, so using Newton's equations of motion, aka SUVET, we are going to demonstrate the practical project and the experiment every 100mm with a ball falling due to gravity. For air resistance will also affect the object that is falling. For objects moving through the air is approximately proportional to the square of the velocity. This depends on the drag equation, which we will use to find the air resistance of both the steel ball and the wooden ball. Fd, the force drag acting upwards on the ball. K is a constant that reflects the effect of the density. Rho, the density of the air around the object. Area is the area of the object or the face of the ball. V squared is the velocity it is moving, so it's going to speed up. At every interval you will notice the ball is actually speeding up every 100mm, which we will prove. D, the drag coefficient, other properties of the object like the surface roughness and the turbulence. So we are basically just going to drop a ball at every 100mm interval between 0 and 1500mm. We are going to calculate then using the SUVET equations and confirm if the results match. Okay, so now we're getting into the fun stuff. What if you drop an object and you can't ignore the air resistance? Then we have a more complicated problem because there are now two forces on the falling object. There is gravitational force and there is also air resistance force. As an object moves through the air, there is a force pushing in the opposite direction of motion. The force depends on the object's speed, the size of the object, the shape of the object, and the density of the air. The part that makes this complicated is the dependency of the air resistance on the speed of the object. Let's consider a ball or a falling object with significant air resistance. How about these balls? When I let go of the ball, the gravitational force causes the ball to increase in speed in the downwards direction. But once the ball is moving, there is now air resistance, force pushing up on it. The force, this makes the net force a little bit smaller, and thus you get a slightly increase in speed. Eventually the air drag and the gravitational force have equal magnitudes. The ball then falls at a constant speed, and this is known as or called terminal velocity. Okay, in order to find the mass of both balls, pine wood and steel, the density of both materials was required. For the drag equation, the density of the air, rho, and the radius, which is 10 mil, a 20 mil diameter ball, was needed. And the drag coefficient of a sphere, which is the round ball, also was needed to find the drag resistance. So the project consists of various electronic sensors and a wooden frame that stands 1500 millimeters tall. As you can see here. Don't let that deter you, the wood, because the system is incredibly accurate, as I will prove. The upright is marked from 200 millimeters right up to 1500. However, when the two sensors is down near each other, when this head's resting on the sensor, they are 100 millimeters apart. It is vital that the upright, the project is leveled using a spirit level. So this spirit level is used to level this or set this upright plumb. So that the balls fall through the sensor during the test procedure. If it wasn't plumb, the ball wouldn't meet the bottom sensor. The feet can be adjusted accordingly to suit. So there's you can put, at the minute I've just got bits of timber in here to level it, but you can put screws in it, and I had screws in it on an ordinary floor. But in the stones, I better with a few bits of timber. So an adjustable head, this head slides up and down the sturdy upright that holds the 20mm balls to test acceleration due to gravity. Both balls, the chrome ball and the pine wood ball. So there's the chrome ball, there you see, there in that wee tray, and there's the wooden ball. Both balls are 20mm in size. They are tested throughout the range. The wooden ball has a small staple embedded into its surface, so it can be connected to the electromagnet. I don't know if you can see it there in the camera. It's very, very small, so to connect it to the magnet here, this is to hold it centralized for this top sensor before it is let go. The ball also has two bits of tape. There's two bits of tape around the ball. There's a hole going right through this ball, so that is for air. The surface area, if the hole's on it, the air can go through it and make the ball travel much faster, which we don't want. We want to do proper calculations and theory on the ball, which you will see later on. This is to limit the chance of drag being reduced as the air passes through it during testing. Believe it or not, this is noticeable during previous testing by a few milliseconds, depending on the height, of course. So the tape on it, the ball goes a wee bit slower, depending on what way the hole is, if it's vertical or horizontal falling. If the hole is vertical falling with the upright, the ball will move much faster. Using an electromagnet reduces, so this electromagnet up here at the top, you can see it there, see, there. This reduces forces exerted into the ball when it is released throughout the first photoelectric sensor. This keeps the ball centered throughout the two photoelectric center beams. So one of these sensors is an emitter and one's a receiver. there's a beam going across there. So when I place the ball, when I get the remote, when I place the ball onto, this magnet's energized now. So this relay here is latched. There's a beam passing from the emitter to the receiver, and the ball is barely touching it at the minute. And if I push this transmitter device, the ball will fall, but we will not do that yet. And so it would be extremely difficult to hold the ball and let the ball go at the exact same time, just above the sensor. So that's the reason I'm using an electromagnet, so I don't need to be near it, and I don't need to put any side forces onto the ball when I let go. The electromagnet is controlled by the receiver transmitter device here at the back. So this transmitter sends a signal to this. Signal goes up this Cat5 cable and into this relay. This relay then delatches, you could say, switches, and breaks the voltage going to this coil, this electromagnet, and the ball falls. Okay, so a highly accurate stopwatch device seen here was used to measure the acceleration of the ball. The device was carefully selected as it measures 1/1000th of a second, unlike many other stopwatches as they only do 1/100th of a second. The stopwatch was dismantled upon purchase, and I connected two low-powered relays to the input pins of the microcontroller device within it. The relay devices pull each signal to ground of the microcontroller within the stopwatch. High precision photoelectric sensors accurately start and stop the stopwatch when the emitted light is interrupted by the falling ball to the receiver at the start and stop positions. The photoelectric sensors consist primarily of an emitter for emitting light and a receiver for receiving light. When the emitted light is interrupted or reflected by the sensing object, such as the ball, it changes the amount of light that arrives at the receiver. The receiver detects change and converts it to an electrical output. The signal is then sent down the Cat5 cable, so these white cables at the back here, to the low powered relay device here. The coils then are energized and the mechanical switch is switched, controlling the stopwatch's microcontroller. So one relay is for the top sensor and one relay is for the bottom sensor. Well, a signal is sent to the radio frequency receiver here using this remote or transmitter. The selected output relay is triggered, so the relay device is triggered in this unit. The signal then is sent up this Cat5 cable to this top relay, which breaks the contact of the electromagnet and the ball falls. So the contact and the relay is normally closed, and it becomes open, and the ball basically just is let go, and this sensor here at the top end is triggered. The ball is being tested, immediately falls due to gravity. The photoelectric beam is broken, or the ball passes it. The ball rests actually within a hairline off these sensors at the minute. And once the ball moves, it just is a fraction in it, and the sensors start immediately. The ball then falls. This instantly starts a stopwatch controller down at the bottom, and this stopwatch starts counting. The ball then falls right down due to gravitational pull, passing to the next Omron sensor, which is this fork sensor at the bottom here. The signal is sent to another low-powered relay, so one of these relays that controls the stopwatch. The ball is then halted by this dampening bottles and falls into this wee tray. We are going to do test in a wee minute. So one of these relays is controlled by one of the photoelectric sensors, and the other relay is controlled by the other one, which is the top or the bottom. These just control the microcontroller of the stopwatch. It's quite simple. So here we are now, we're going to do a test run at 1000 millimeters. And the camera is running, the ball is on, ready to rock. So there, we're going to do it right now. So it should work around about 452, I think, milliseconds. So here we go. Will we show the ball falling? Remote, trigger. Okay. So we got 453. We're going to run it straight away now. So hopefully we get the same result to show the accuracy of the device. So we have to reset the timer again. Right, away we go. So we got 453 milliseconds again. We're going to do it one more time. No, actually, we're not. We're going to put the wooden ball on and see if it takes longer. We have to see if it takes longer for it to fall because of air resistance. You might notice a wee difference. This is not easy to put on. Hold on, 2 seconds. Please stick. Hold on, I should have stopped it. So the wooden ball is on and it's hanging on for dear life. It took me a couple of attempts trying to connect it because the filing is so small in the ball. If this was outside, it would not stay on. The wind would just blow it off. So the steel ball took 453 milliseconds to get between 1 meter, or falling at a 1 meter distance. So we're going to see how long the wooden ball takes now. So here we go. It took 454, a millisecond longer, probably because of air resistance. We'll look at calculations later on. So we will. I'm not going to try and run that again because it takes a long time to connect the ball onto the electromagnet. The volume of metal within the ball is so minute. It's basically just a filing, and I actually stood for about 60 seconds trying to connect the ball on there 1 minute. So it's handier putting the steel ball on, so I'm going to run it now again with the steel ball just to show that the steel ball will fall faster. So here we go. Energize the coil. If the coil is now energized, just place the ball on. So in the center roughly. So the unit hasn't been touched, it's still 1000 millimeters. Reset the stopwatch and trigger. So it took 453 milliseconds. I would love to try and connect the wooden ball again just to show, but I might just give it one go. One go. Right. If it doesn't work, I'm going to give up. I'll spend 10 seconds on it anyway. Right. Come on, please connect. Does not want to connect at all. There we go. There we go. It's hanging on for dear life, right? Reset the stopwatch. Trigger the ball. Hopefully it doesn't fall off. Right, okay, so the steel ball was 453 milliseconds. Let's see what the wooden ball falls at. Oh, 458 that time. So it could be down to air resistance. Or more likely it is down to air resistance. Now we're going to do the steel ball one more time, as it's so easy to do. So energize this electromagnet. It is now resting on the beam, the top, just at the point of them beams breaking the beam. Reset the stopwatch, and away we go. Four, 5, 3. So you can see that the system is very accurate. I'm going to do one more test now, and the test is going to confirm. I might do a 1400 millimeter run on the steel ball to confirm the theory calculations. So here we go. I have moved the head unit up to nearly its maximum point. I can go to 1500, but I'm going to do a 1400 millimeter run. So you can see at the pointer there is bang on 1400. The ball is on, ready to rock. So hopefully it should fall and back up theory calculations of 1.4 meters, which is 534 milliseconds. So here we go. We're going to. That's a bit more impact now. Going under these bottles, or these dampers I call them. So hopefully it doesn't hit me. So hopefully the stopwatch starts and stops at 534 milliseconds, which is what's on my hand there, at 1.4. So here we go. 535. Okay, so it took a millisecond longer. Could be to do with the distance of where I have the pointer on this, but I don't think it is. I think it's probably down to air resistance. I'm going to run it one more time here to show where the camera's running. So I have energized the coil, electromagnet. The ball is on, ready to rock. And strike the bottom sensor to stop a stopwatch, reset it then, and we're going to run it again right now. So it was 534 or 535. Theory is 534 milliseconds. I hope to see around the same thing again. So it was 535. So you can see now I've done test runs at 1 meter and I've done test runs at 1.4 when the camera is running. So the system is highly repetitive, very accurate, very interesting in my opinion. Really good. I could try and put this on here. I can try it. Let me see. Oh, I have to energize it first. Bear with me 2 seconds, please. If this was on, it'd be interesting because you could see it when the camera was running, but I don't think it's going to work too well. Please connect. So the ball is now connected. As you can see, I had to get a jar, a thinner's jar to stand on, to place this ball on this magnet. It was really took me a wee minute to connect. It's still not centralized, but if I touch that ball now, it would just fall off, or if I even breathe on it. So the head unit is still at 1400 millimeters. Now with a wooden ball, you should notice a big difference. Because of the height now, air resistance is going to come into effect with the lighter ball, lighter mass. The steel ball took 535 milliseconds. So this ball should take longer. In theory, it should take longer to drop. So here we go. Hopefully it's actually plumb, the ball falls through the sensor at the bottom. Okay, so it did. So you can see there that the wooden ball took 538 milliseconds, which is 4 milliseconds more to fall, which is quite interesting in my opinion. I like this project, I really do. So simple but so efficient, so effective. So that is it. Hope you enjoyed. I'm going to actually take this project into bits now and take all the parts off it again. And I might build a vacuum chamber in the future. But I think this is more interesting, adding in air resistance, using the lighter balls. Here in this table we see all results, theory and experimental, using Suvat equations transposed to find the time in milliseconds. The column on the left is the number of intervals tested throughout the range, every 100 millimeters. The experimental results match the theory calculations very well as seen, especially with a steel ball. The air resistance was not very noticeable on the lower range, however it could be seen whilst experimenting with the wooden ball throughout the higher range. The force acting up on the ball was taking effect at around 1 meters or 1000 millimeters. This can be seen in the next image. It was clear during the experiment that the velocity of the falling balls was accelerating with distance over the 100 mil intervals. Both the theory calculations for velocity and practical velocity results were much similar. The steel ball was hitting the surface, or the bottle dampener I made, at a much higher impact as in the demonstration. Here in this table we see theory results using the drag equation to find the negative acceleration caused by air resistance. When the 20mm balls are in free fall, the drag force is very small throughout the range. However, if the object being tested was cube shaped or flat placed, the value will be much bigger as the drag is increased. The negative acceleration in the columns on the right are found by dividing the object's drag by the object's mass. The ball's drag takes a much higher effect on the lighter ball would as the force acting up becomes closer to the gravitational pull of the Earth. So you can see in the results here that the wooden ball and the steel ball, and also the theory calculations denoted by the black line. Air resistance has small effect on both balls. On this slide we can see negative acceleration vs velocity of both the steel ball and the wooden ball. We can see that air resistance has little effect on the steel ball at 5.5 meters per second. However, with the wooden ball we can see that it is slowing down much faster. The force acting up in the wooden ball, air resistance is becoming equal to the force acting down, so the ball's weight. This is taking effect much faster. We will do calculations for terminal velocity at the end and see what happens. This plot shows the drag force of a sphere falling freely due to gravitational pull for a radius of 0.1. Okay, so near the surface of the Earth, an object in free fall in a vacuum will accelerate at approximately 9.8 meters per second squared, independent of mass. With air resistance acting on an object that has been dropped, the object will eventually reach a terminal velocity, seen in the calculations below. Eventually the drag force equals the weight force. The forces will then become balanced and the ball ceases to accelerate and travels at a constant velocity towards the surface of the Earth. The maximum velocity reached by a falling object is called terminal velocity. Therefore, both balls, and the wooden ball and the steel ball, will eventually fall at a constant rate. The wooden ball will meet its terminal velocity much sooner at approximately 14 meters per second, as its weight is much less than the steel ball. The steel ball's terminal velocity is 60 meters per second, which is approximately 135 miles per hour. Please subscribe and like for more interesting videos. Thank you.